before starting, I would like to thank the scientific committee and the FIFA for giving me the opportunity to present my PhD thesis here today. So, well, I'm not an anti-doping specialist. My thesis is not dealing with anti-doping. But, and as you can see, I'm working at the Institute of Forensic Science in Lausanne. But according to what I heard today, I think that my thesis fits pretty well in the future perspectives for the anti-doping fight. In the sense that, for example, with the future introduction of the steroid passports and the monitoring of individual athletes, and in the sense also in the feeding of a common database with results coming from different analytical methods or coming from different laboratories. So the purpose of my talk, if I have time, is to show you that in the context of illicit drugs chemical profiling, we had some questions were rising. And I think that the approach we applied, or the questions that were rising, you could have similar kind of problems. So some people already talk about intelligence. I won't go too much into details because I know that the next speaker will discuss deeply about this. But just to say that in forensic science, databases are really important. They play, they really have a central use in the whole process. So basically, from data, we will extract information, we will store it into a memory, the database. In this memory, we will try to find matching cases to provide intelligence in the sense to explain a phenomenon, for example. So this process applied to the illicit drugs chemical profiling looks like this. In my laboratory, to determine the chemical profile of real polyseries of heroin or cocaine, we use GCMS analysis. The problem we have to determine the profile is that we don't have reference standards; they are not available. So we don't do formal quantitation of the compounds, but more a semi-quantitation, and we work on peak area values. So you have here an example of a chemical profile. So again, this information, the profile, is stored into the database, and the idea is to perform queries in this database. And especially in the context of the illicit drugs trafficking, the idea is to get knowledge about the structure and the organization of the distribution networks. Every lab working with a database is faced with two main problems. One, which is related just in the context of one laboratory, which is called intra-laboratory here. Actually, it's, for example, you use a method to feed a database, but then you have to change this method. You want to apply a more efficient method, or for whatever reason, you have to change this method. The second one is a bit more complex because you have, okay, it was automatic. The second one is more complex in the sense that you have also the aspect to share your database with different laboratories. So for both problems, you have a number of questions. Are my results similar? Of course, before merging results into a common database, you have to be sure that they are reliable, that you can compare them. But then, in the context of a database, what does it mean to be similar? And one question also is, if you can assess that the results coming from different laboratories are not similar, can you improve this similarity before introducing them in the same database? Of course, we are dealing with a different analytical method. But what does it mean? So in this study, we decided to define an analytical method with according to 3 levels of analytical parameters. So basically, we say that analytical method could be defined by its analytical technology of separation, detection, then by the brand and the model of the analytical instrument, and then by parameters of analysis which can be modified from one injection to another one. For example, in GCMS, you will have here the flow rate or the event program. Here you will have the scan range, for example. So the purpose, one of the purpose in this thesis was to estimate if any analytical difference would be of significant influence related to the similarity of the results. Basically, if we have 2 methods different to the brand or the model, is it really an issue for the similarity of the results? Or is it not an issue? So of course, you have then to define a methodology able to assess and estimate the influence of these parameters on the similarity. And methodology which must take into account the context of a database which is daily growing and growing by the addition of new results. So about the analytical strategy, of course, from a method of reference, for example, the GCMS in my lab. So I use the word of method of reference because that's the one we are daily using in the laboratory. So from any method of reference, you can be faced with a huge number of different analytical methods. So we decided, using the previous definition I show you, to say that all these possibilities could be included into 5 scenarios. So the idea is to say that, okay, the first scenario, the closest one from the method of reference, means that we will have just a change in this parameter, and so on. The second one in the model, then the brand. So from a theoretical point of view, we will say that the scenario 1, so the method developed in the framework of the scenario 1 will be more similar to the method of reference than the scenario 5, basically. So practically, the idea was to take our reference database, so all the samples analyzed with the reference method, to have a representative sampling, representative in our context, in the illicit drugs chemical profiling context, means samples coming from different chemical classes, some that are linked or not linked anyway, and then to analyze them with each scenario. Then, using some statistical tools, after their introduction into the database, the idea would be to check how similar are the results. Once again, with the idea to estimate if every analytical parameter would have a significant influence on the similarity. Of course, if not, that would mean that it won't be necessary to apply strictly the same analytical method to feed the same database. I'm pretty quick, so I think I can drink a bit. So, in the context of a database, what you have to ensure is that the structure of the data is saved. So, of course, your database is always moving. But what we mean by keeping the structure of the data is that if I analyze the same sample with different analytical methods, here are the 5 scenarios, I will expect, if the analytical variability is low, that I will get the same information meaning that these results will be grouped into the same chemical class, in my case of illicit drugs chemical profiling. Okay, but how to do this? We say that first we could try to optimize the similarity. And I will show you later. We did this using a mathematical adjustment. But then, okay, you optimize the similarity, but how do you know that you optimize the similarity? And as I said previously, how to estimate this similarity in the context of a database? Here we use a clustering-based tool. Okay, I won't go too much into detail to explain this illustration. You saw the profile at the beginning. Or basically, for heroin, we get 6 compounds. So 6 numerical values which characterize this sample and which plays the role of the chemical signature for this sample. So the idea is to mathematically correct each variable for each compound to make it as similar as possible to the reference method. So the idea will be to analyze the sample with another method, then to correct it mathematically, and then to obtain a reference-like profile, which means that it will have been the profile we will have obtained if we will have analyzed this sample with the reference method. Then to check how similar were the reference profile and the reference-like profile, we use some chemometric tools. Here are the tools. So for every sample from the sampling we made, we analyzed them with each scenario. Then we introduce one by one the reference-like profile and the reference profile into the database. And then we check after clustering if they were close according to distance value, let's say. So the idea was then to check, well, basically, if they are similar, they will be separated by a really low height value. If they are not similar, they will be separated by a really high value. So you can see, something I could precise that as you do this for all the samples, then you can get a performance value to estimate in general the quality of the similarity of the results for each scenario. And if you remember the 5 scenarios I show you, we will expect a better similarity for results coming from the scenario 1, because this one, from a theoretical point of view, is pretty close to the reference method, because just just one parameter was changed. So here are the results. So if my results coming from different methods are perfectly similar, we will have a horizontal line. So here you have the distance value. So here you can see that for the 2 first scenarios, which were, in this case, actually that's the scenario of harmonization of methods, where you have exactly the same methods and 2 physically different instruments. Here that's a fast GCMS compared to a GCMS. So here you can see that actually results are really similar, in the sense that according to the tool we made into the database, they are really close. I mean, the reference profile and the reference-like profile are really close to each other. So that's pretty interesting, because that means that finally, with another method which is more efficient, because I have fast GC compared to GC, my results are really similar, because they are grouped in the, they are almost at the same place into the database, taking into account that in my database I have hundreds of different samples. So the 2 next scenarios. So here it was a comparison between GCMS on one manufacturer and GCMS with another manufacturer. and here it was GCMS compared to fast GC-FID. So you can see that for these two scenarios, we have a pretty similar performance value. So, okay, you can see the difference with the two first ones, but pretty quickly, we have a huge increase, a quick increase of the performance. And since value of 5, we are pretty close to the 1% of performance. So the last scenario, which was a comparison between GC and LC, we have, of course, less similar results. So finally, according to the results, we have kind of, how to say, the 5 scenarios which have been established from a theoretical point of view are kind of confirmed according to the results, in the sense that, yeah, the scenarios which are from a theoretical point of view closer to the reference method, from the reference method, get, well, for these scenarios, you get really similar results. According to some tools that I won't discuss today, we say that a difference, that if two methods were different according to the analytical technology of separation and detection, that the analytical variability was then too important, and that a mathematical adjustment was not enough to reduce this variability. But for the other ones, possibilities were, well, there were possibilities to say that we could feed a common database with different analytical methods in function of the reliability you expect, of course, from your methodology. I'm just finished. So I don't want to prove that this methodology is the one you should apply in your case, but just to show you that that we developed a methodology to assess the similarity of analytical results, even if they were coming from a wide range of analytical methods, and especially in the context of database, where you have to take into account this specific use of the database. For us, this could be used in, or at least tested in other topics. For us, in the context of the illicit drugs, in the context of the fight against the illicit drugs trafficking, that could lead to a better exchange of results, and then to provide some intelligence to better fight against this trafficking. So I would like to thank some people who participated to this thesis, and you for your attention.